We're going to start with kind of a review of ODE theory. I'm going to introduce hopefully a good amount of notation that is used in ODEs as well as in partial differential equations, which is what we want to get to hopefully in the next 2 or 3 weeks. So I will start by discussing the derivative, and I won't spend too much time on this, but we're doing things very generally. So what we do is we say, let X be a subset of Rn. And what we're going to do is we're going to define a map, so a vector-valued vector map from this subset X to Rn. If this map is linear, of course, we can just represent it with a matrix. But this is including any kind of nonlinear map we want to talk about. The whole motivation here is to discuss things like systems of ODEs. So once we have this, we can discuss the idea of a derivative in kind of a very formal fashion. We assume y is very small, and we let f of x plus y be f of x plus ly plus some remainder term. Sorry. And we say that this is a derivative if it satisfies that as y gets very small, this is the norm of y. This norm, since again this is a mapping from Rn to Rn, this norm here that I'm talking about is the Rn norm. If the limit, right, as this approaches 0 of this remainder term divided by y. Again, this remainder term is in Rn because that's where all of these things are being mapped to. But this bottom term, this y, is in Rn. So the norms are the Euclidean norms, the sum of squares, but we are talking about 2 different spaces here. Again, trying to be as general as possible. If this is 0, this is our definition of derivative, and we call our derivative this L. We can motivate this, and we can kind of see this. If we pretend these are not vectors, or not abstract maps, we can see this as exactly f of x plus y minus f of x divided by y being equal to L plus our remainder term. Of course, division by a vector doesn't make sense unless we're talking about Clifford algebras or something like that. So we use this kind of formal notation and we discuss norms. This would work if we sort of take a norm of both sides. Either which way, this is what Taylor presents. This L here is our derivative. So this L, by the way, if you notice, these are all vectors. These are all objects in Rn. So this L is not a constant, but this L is a vector map just like X is. I'm sorry, just like F is from this open subset to Rn. So this L we denote by d of F, and we can write it this way. And can anyone tell me what that's notation for?
It's for each variable.
It's the Jacobian. Right, so one way to kind of see this, assuming m rows and columns, is the Jacobian of partial derivatives of each of the elements of this vector-valued function. And then I'll just write the last. So again, this is just the Jacobian that hopefully everyone's seen before. This is just the derivative, a formal way to kind of motivate it. And I'm not going to go through any of the proofs or any of the sort of discussion here, but all of the properties of the product rule, chain rule, etc. hold. I'll just state the chain rule to kind of show that. So if we have 2 of these maps from an open subset of Rn to Rm, we call them f and g. If we compose them and take the derivative evaluated at a vector in this capital X, we can write this as the derivative of f applied at this. And so this can, again, because these Jacobians, these derivatives are matrices, we can view this as matrix multiplication and the derivative of that multiplied matrix times the Jacobian of this f function. So this is, again, just the chain rule using this formal notation. from a map from a subset of Rn to Rn.
Can I ask,
Yes.
what do you mean by dividing by y?
I was talking about this. This isn't at all correct. I was saying that if we look at this as kind of the derivative that we see in a calculus class and take limits, we can motivate why this is written this way. But of course, I said you can't divide by a vector. This is not mathematically rigorous. It was just sort of motivating this definition. Because the first time I read this, I did not immediately recognize that it was, in some sense, a rearrangement of the norms.
Does that have to be G by chain rule instead of F?
Does this have to be what?
Like G, F, G, and then multiply for the G, X
Unless I
instead.
wrote it down in here. Which is possible. And I don't seem to have that.
I think the
Oh,
second one is
you're right.
G, yeah.
Yeah, no, you're right.
No, but the
No, the
other
second
one,
one.
the other one.
This here?
Yes, that must be
Okay.
G.
Yeah. Right, that's what I have written down. I have the F's and the G's switch, but this, okay. So moving forward, what we're going to talk about now is kind of a different idea. It's the notion of a multi-index. And this is used in this discussion of ODEs, but it's used very prominently from what I can tell in PDE theory. It's used in every paper I've read except for those that talk about specific equations. So what we do is we take an element, again we're discussing a map from Rn to Rm, and we take an element alpha in Rn, but we're careful about how we define it. We say that alpha is equal to alpha 1, alpha 2, alpha n, where alpha I are positive integers or 0. And then what we can talk about is first I'll discuss it for just polynomials. If we have a vector x, so this vector is x1, xn, in this n-dimensional space, we can say that raised to the alpha, or sort of taken to this multi-index, is just, if I have this right, this vector so it's just this, this vector with each of the components raised to this power. This is useful for what I'll do in a minute, which is kind of discuss Taylor series. We have this notation, which I will just sort of remind everyone. Hopefully everyone's seen this. Just to represent the derivative in one direction with respect to one of our independent variables. So kind of combining these ideas, what we do is we talk about the derivative of this f and this is equal to each of these derivatives with respect, that's one, an alpha I derivative of each of the I independent components, which we can write just as this. We define the order of this alpha to be the sum of each component. Since these are all positive integers, we don't worry about sign or anything like that. So does this kind of make sense? Is this confusing to anyone in terms of this notation? Okay, so again, this is used quite a lot, and it allows us to do some fairly powerful things. One of the things it allows us to do is, we won't do it here, and I'm not sure if it's done in the Taylor book, but I have seen PDE papers where they discuss weak derivatives or rational value derivatives. So if we kind of loosen that notion that these alpha I have to be positive integers, we can say, okay, alpha I have to be positive rational numbers, and then we can discuss rational derivatives. I'm not going to go any further in this, I'm just saying that this notation perfectly expresses that concept. So it's another use of it. What we will discuss is how to write something like Taylor's theorem given this notation. So first off, does anyone want an example of this multi-index, or is it very clear what I mean? So I'll take that to mean that it's very clear and no one has any questions about it.
Nobody said yes.
Okay. So we'll talk about Taylor's theorem. This is, of course, the multivariable Taylor's theorem. We defined F as we have before, a map from an open subset of Rn to Rm. And we can just write down in this multi-index notation something like this.